All right. Now, so that I can, talk about the symmetry of these two graphs, we're going to do this on sine. We need to basically, instead of just doing one period, let's do two periods. Okay. Most of the time when we graph, or when you graphed like on your graphing test, you only did one period. But we had the understanding that these graphs go on forever, don't they? Okay. They don't just do a little snippet. We just do a little snippet so we can understand a part of it. Okay. And that's really all that we need. Now for symmetry though, I'm going to need a second cycle, and I'm going to have to go on the other side of the y-axis for sine. All right, so help me over here on the other side of sine. Okay, where would the graph be at negative pi over 2? Yeah, negative 1. Okay, good. And back at 0 at negative pi, up at positive 1, back at 0. Okay, I'm not used to drawing them backwards too well, but there we go. Okay, now tangent, all I really need on tangent is one period, because tangent was the only one that we offset, right? Okay, now let's answer this question. Okay, don't worry about copying down these graphs. Sorry, probably should have told you that like 2 minutes ago. All right, don't worry about copying them down the graphs, because we know what the graphs look like, right? Okay, I'm just putting them up there so we can answer the question, how are they symmetric? Right. All right, y'all see it? They're symmetric with the origin, aren't they? Okay, now this is bringing up some old algebra stuff we were talking about back in like October. All right, remember that? We talked about symmetry of graphs. Okay, so it's coming. Now, no. So the x-axis, oh, that sucked. This is going to take forever to reboot. I hit the switch. I'll pause this. All right, so here we go. All right, now you said the x-axis. All right, let's look. Like if sine was symmetric with the x-axis, it wouldn't be a function, because no functions are symmetric with. See, if it was symmetric with the x-axis, you'd see something like that. Okay, because then it would like fold over right there. Okay, all right, but all right, Dariana said it. They're symmetric with the origin. Y'all see the symmetry? Remember how if something is symmetric with the origin, then you could flip it across the x and the y-axis. Okay, so imagine you could take like the top part of the sine curve and flip it across right here, and it would look like this, wouldn't it? And then you could take that part and flip it across the y-axis, and it would line up, wouldn't it? Okay, so both sine x and tangent x are symmetric with the origin. Now, so what do you think is going to happen with cosecant and cotangent then? Yeah, they're going to be symmetric with the origin also. Okay, now let's look at the graph of cosine. Okay, and let's ask about the symmetry there. Okay, so in order to get the symmetry, I'm going to need more than one period. So I'm going to do one period on the right of the y-axis, and now I'm going to do one period on the left side. So y'all help me fill in the left side. It would go down to 0, and then -1, 0, and 1. Okay, so let's see if y'all can recognize any symmetry here. Right, cosine is going to be symmetric with the y-axis. Okay, so let's see if you can figure out if cosine is symmetric with the y-axis, secant is also going to be symmetric with the y-axis. Okay, now let's talk about, well, what does all this mean? And see, everything I'm doing in this unit, I'm trying to relate back to the graphs. See, all this stuff wouldn't have made sense to you if you didn't know what the graphs look like. So that's why we did that graphing unit previously. All right, so y'all remember this? Odd functions, what am I saying there, are symmetric with respect to the origin. So this is sort of the graphing interpretation. Now this probably, you need to write this part down, okay? All right. So odd functions are symmetric with respect to the origin. Now, y'all remember what it looked like algebraically? And this is what the algebraic part is really what we're going to apply, not so much the graphing part. The graphing part leads us that it's symmetric with the origin. And now that means that f of negative x is equal to the opposite of f of x. Okay? Remember I gave you that question, I think, on 2 different tests. Okay, I gave it like to the regular test and the 6 weeks test. So it was a multiple choice question. I'll probably give it to you again. Okay? Because this is something good to know. You'll use it, you know, in several different math classes. All right, even and odd functions. Now, so this part, if we know a function is odd, we know f of x should equal the opposite of f of x. Now, where this is going to help me is with negative angles. Okay, see how those angles are negative? Now, what we used to do with negative angles is we would find a coterminal angle. Okay, but what we can use are these even and odd properties so that I don't have to do this. So if I have the sine of a negative angle like this, y'all see if y'all can tell me what's the right side going to say there? It's going to say, what's going to be in front? Negative sine of x. Okay, so sine of negative x is equal to the negative sine of x. So instead of putting the negative sign on the angle, we can just put the negative sign out front. And let's talk about, well, why do we want to do that? Well, on our unit circle, we usually think of our angles in a positive way, don't we? Okay, instead of a negative. So what this does is it bypasses finding a coterminal angle. So I don't have to find any coterminal angles anymore with negative angles. Okay, I can just change it to a positive angle and throw the negative out front. Uh-huh. All right, you said pi over 4. Okay, so if we did this, if we said the sine of negative pi over 4, like that, then this just would equal the opposite, or the negative of the sine of pi over 4. And the advantage is that it's a positive angle. And so I find the sine of pi over 4, whatever it is, and just say the negative or the opposite of it. Okay? Now, do y'all see how the other ones are going to follow here? So the cosecant of negative x is going to be negative cosecant of x. Okay? Tangent of negative x is just the negative or opposite of tangent of x. All right, why do we say these? Because we said all these were symmetric with the origin, right? So if they're symmetric with the origin, that means they are odd functions. Okay, so out of my 6 trig functions, these 4 are the odd ones. Now, the best way to learn the even and the odd functions, or your trig functions, is to remember which 2 are even. Because if you can remember which 2 are even, then you say, well, the other 4 are odd. Okay, so these are the other 4. So now let's look at the even ones. Okay, can I switch it over now to my even ones, y'all okay? All right, so my even functions, we said were these 2, right? Cosine and secant, because they were symmetric with the y-axis, right? So y'all remember this part here? That's what makes, algebraically, what makes a function even. F of negative x is just equal to f of x. Okay, the way I relate to this, probably better than anything, is to think about the graph of y equal x squared, which is parabola, right? Now, that would be an even function, wouldn't it? All right, so if we looked at y equals, or f of x equals x squared, all right, what's f of 2 going to give me? 4 is what 2 squared is 4. Now, what's f of negative 2, though? Still 4. All right, so that gives me that symmetry with the y-axis there. And I always think of that one because it's sort of an easier one to think about. So now, let's see if you can kind of fill in the blank here where I've put my shade there. Okay. Right. So cosine of negative x is just cosine x. Okay. And then, so secant would follow because it's the reciprocal. So secant of negative x is just equal to secant of x. Okay. And all this is, these are called your even and odd properties. Okay. So what we have is that cosine and secant are even, so the other four are odd. Okay. And what these help me do is usually work with negative angles. So I don't have to change them to positive. Remember how if we had a negative angle like in degrees, if it was like negative 290 degrees, we would just add 360 to it? Well, that can cut out that step. Okay. Now, let's look at some examples of this. All right, have your unit circle in front of you. Okay. So now, instead of actually going to negative pi over 6, let's just rewrite this so that this angle is positive. Okay, so would I put negative cosine of pi over 6? No, it would just be cosine of pi over 6. And what's the cosine of pi over 6? What, square root of 3 over 2, is that right? Okay. All right, so did y'all follow? Because what did we say about cosine? Cosine is even. Okay, which other one's even? Secant. And that's what I remember. Cosine is even, secant is even. The other four are odd. Okay, so now let's rewrite this one. Instead of having a negative angle and having to find a coterminal angle, right, this will be opposite of sine of 7 pi over 6. Okay, so now let's look on our unit circles. All right, what's the sine of 7 pi over 6? Negative 1/2. So if that's negative 1/2, the opposite of that would be positive 1/2. Okay, talk to me. Did y'all follow that? Okay. Yeah. All right. So let's look. All right. You see where 7 pi over 6 is? Okay. So, all right. What's the sine of 7 pi over 6? Negative 1/2. Okay. But if we have negative 7 pi over 6, we can just rewrite this as the opposite sine of 7 pi over 6. So the sine of 7 pi over 6 is negative 1/2. But then the opposite of that would just be a half. Okay. All right, let's look at, well, secant really wouldn't be a good one, but let's look at it. All right, secant of negative pi over 3. Now, again, let's rewrite it. Okay, so is this going to be, all right, secant of pi over 3, or is it going to be negative secant of pi over 3? Right, because secant is even. Okay, now, so let's go to pi over 3. Pull this down. All right, so at pi over 3, how do we do secant? Reciprocal of cosine. So cosine is 1/2. So it would be just 2. All right, that's it. All right, let's look at this one. Now, I'll mess with you here. Right. Well, I guess I really didn't mess with you then. All right, so now the negative in the front this time. All right, so now this would be, if I change my angle to positive, now this is an odd one, right? So that's just going to change this to positive, right? So this would just be the same thing as the tangent of 2 pi over 3. Okay, so look at 2 pi over 3. All right, yeah, the tangent at 2 pi over 3 is negative square root of 3. Okay, now just to compare, all right, what if I had it without that negative in the front? Yeah, it's just going to be, let's see. So the tangent of negative 2 pi over 3, how can I rewrite that? That would be the opposite of the tangent of 2 pi over 3. Right. And so the tangent of 2 pi over 3 is negative square root of 3, but the opposite of that would just be square root of 3. Sure. Okay. All right. Let's do the secant of negative pi over 6. And we throw a negative in the front. Okay. All right. So now secant is even, right? So when we change the pi over 6 to positive, does that mean we throw a negative to the front? No. So it would stay negative, wouldn't it? It wouldn't change to positive. Now, let's see. What is the secant of pi over 6? Well, the cosine is square root of 3 over 2. So the secant would be 2 over square root of 3. Okay. Nuh-uh. Because secant is even. All right. Go back to this one. But we wrote secant of negative pi over 3 is just secant of pi over 3. You don't throw the negative to the front there. Okay? Because secant is even. All right, let's do this first, okay? Let's come back to this one, okay? Let's do this. All right, so what would that be? Just secant of pi over 6. So I don't throw a negative in the front there, do I? Okay, so now what's the cosine of pi over 6 is square root of 3 over 2. So the secant would be 2 over square root of 3, which if I rationalize it would be 2 square root of 3 over 3. All right, it's going to be negative. All right, so watch. This one's got negative secant of negative pi over 6. Think of it this way. On the odd functions, what basically happens to the negative sign? Even though this is technically not what happens. Right, it comes to the front, doesn't it? But what happens on the even ones? This just changes to positive. So is that going to change that? No, it's still going to be negative. It's going to be negative secant of pi over 6. So we just said the secant of pi over 6 is 2 square roots of 3 over 3. So with a negative in the front, that would just make it negative. Negative 2 square roots of 3 over 3. Is that better now? Okay. Good job, teacher.
So,
all right.
Okay, can you move it up that negative table there?
Uh-huh.
So like you're sending that negative 2 pi over 3 over there.
Right.
That's what makes it positive.
So it makes it positive.
That's on an odd one.
Right. That's the odd one. So on the even ones, the negative just disappears on the angle. Okay. And it kind of comes back to this, all right? Think about this. I want you to think about pi over 6 and negative pi over 6 on your unit circle. Okay. What's the cosine of pi over 6? All right, square root of 3 over 2. What will be the cosine of negative pi over 6? Square root of 3 over 2. Same thing. Okay. And so that symmetry of the y-axis is what makes cosine and secant do that. They're even functions. Okay. Now, so we've talked about, all right, again, the even functions were cosine and secant. So the odd ones would be the other 4. All right, now, let's talk about this idea. Okay. Trig functions are what we call periodic. Okay. And so that's what's our root word there? Period. All right, so we talked about, this is again relating back to the graphs. Everything I'm doing is relating back to graphs. So we said with sine, cosine, secant, and cosecant that the period is 2 pi. But with tangent and cotangent, the period was just pi. And so what that meant, and like on sine and cosine, we would only do one cycle, right? We would only do one period. How come we only did one period? How come we wouldn't keep going? Right, because it would just repeat, wouldn't it? All right. So when we say that the trig functions are periodic, all they do is they just keep repeating themselves. So after I've completed a cycle, the next cycle would just start back over, right? Okay, it would just leave off or pick up where the other one left off and do the same old values, because what did sine and cosine do? Bounce back and forth between -1 and 1. Okay, so they would just repeat those same values over and over and over. Now, we're going to use this to evaluate some of these, especially if I'm adding a multiple or even multiple of pi or an odd multiple of pi. Okay, now here's another way to look at it. Instead of the graphs, look at it in the form of the unit circle. Okay, let's talk about a tangent here. All right, so let's talk about the tangent of pi over 4. The tangent of pi over 4 would be 1, right? Okay, now what about this? Notice, where else is the tangent 1? Right, at 5 pi over 4, it's also 1. Now, see if you can picture this, okay? Right, notice they're across from each other. Notice it visually. What is this distance right here? Pi, because it's what? Halfway around the circle. So if I go a distance of pi, tangent just starts over, doesn't it? That's where we get the idea that the period for the tangent function is just pi. Okay, now let's talk about cosine just a second. Let's go to pi over 6 right here. All right, what's the cosine pi over 6? 3 over 2. Okay, now what if I did the cosine of pi over 6 and I added 2 pi to that? Now, if you added 2 pi, how far around the circle is that going to take you? If I start here and add 2 pi, it's going to go, yeah, all the way around back to the same spot. And so the cosine of pi over 6 plus 2 pi would still be square root of 3 over 2. It just cycles back over. Okay, so here's sort of the bottom line here. If you have y equals cosine of x plus 2 pi k, then that's just the cosine of x. Okay, now the way you think about this, 2 pi k, just think of it, this is a multiple of 2 pi. Okay, so what happened when I added 2 pi? I just went all the way around the circle, didn't I? Okay, what if I had 4 pi? It would just go, what, all the way around the circle 2 times, and it would be back where it started with. So if I take my angle and I add, this is what cosine, all the ones that have a period of 2 pi, okay? If I add a multiple of 2 pi, it's just the same thing as just the cosine of the angle. All right, look at tangent. Now notice, how come on tangent I didn't say 2 pi k? Because the period's just pi. And so this would also follow for what else? Cotangent. Because tangent and cotangent have a period of pi. Okay, so these are what's called your periodic properties. Okay, because sine and cosine, all the trig functions are periodic, which means they just start over at a certain point. Okay, now let's apply this. Okay, so what I can do with tangent and cotangent is add any multiple of pi, and it's just the same thing. Now with cosine or sine, though, I would have to add an even multiple because the period is 2 pi. So what is really just the tangent of 3 pi over 4 plus 7 pi? It's just the tangent of 3 pi over 4. Okay, what is the 7 pi going to do? It's just going to go around the circle 3.5 times, isn't it? But it's going to arrive at the same tangent value. So if I add a multiple of pi to tangent or cotangent, it's the same thing. Now, what is the tangent of 3 pi over 4? -1. Okay, so what about this one? Cosine of 7 pi over 6 plus 14 pi. So that would just be the cosine of 7 pi over 6. All right, y'all think about it visually on the unit circle. All right, So let me show you. If I'm at 7 pi over 6, where's 7 pi over 6 at? Third quadrant. Okay? If I went 14 pi, what is that actually doing from that spot? It's going around in a circle. How many times would it? 7 times, wouldn't it? Because 7 times 2 pi would be 14 pi. So if I went around 7 times, you would still be back at the same spot, wouldn't you? And the cosine would still be the same thing. So cosine 7 pi over 6 is what? Negative square root of 3 over 2. Is to recognize this later when we solve equations, that that's just really the cosine of 7 pi over 6. Is to make something that's kind of difficult looking, make look simpler. Okay? That's the whole point. Yeah, it'll be later. Okay, because this is really a simple thing. Now, look at this one. I made it look hard, but
Pardon the interruption, one more thing. Students, we just got 300 more tickets for the game tomorrow night. Once those are gone, that is absolutely it for here. You'll have to buy them out at ULM. Just again, a reminder, Coach Jones asked me everyone where Cardinals game tomorrow night. And again, my suggestion would be to arrive early.
all right. Now, here's the key. Does it really matter that it's minus? No, that just means you're going around the circle, yeah, clockwise instead of counterclockwise. Okay. Now, what's important is this: what kind of a multiple of pi is that? It's an even multiple of pi, isn't it? Because 4 is even. All right. So this would just still be the same thing as the sine of 5 pi over 6. Yeah, with hang on, let me finish this one. Sine of, what is the sine of 5 pi over 6 now? All right, a half. Okay. All right, back on the first one. On this one, all right, on tangent, you remember what was the period for tangent? Pi. Okay.
We need Virginia Massey to check out.
Now, so if I add any multiple of pi to my tangent angle, it's just going to be the same thing.
Oh, so that's
Okay.
why. Okay, that's why it's the one that you can.
Right. Even doesn't have to be tangent because it has just a period of pi. All right, go back to the example that we pointed out. All right, look at pi over 4. Okay, the tangent there is 1. Now, at 5 pi over 4, the tangent is also 1. So if I go from pi over 4 to 5 pi over 4, you're going halfway around the circle, right? And halfway around the circle is just pi. Okay? That's where we get the period of the tangent function from. Okay? All right, let me give y'all a worksheet here before you leave.